Hello everyone, myself Vishwadeja. Today we are going to discuss operating system project. So operating system project 2. In the operating system project 1, we have discussed about the Nand to Tetris and executed some of the basic gates like AND, OR, XOR, NAND, etc. In this video, we are going to execute some half-adder codes and full-adder codes of HDL into the hardware simulator 2. Now let's go into the video. In this video, our objectives are binary numbers, that is representing binary numbers, adding binary numbers, etc. Then binary addition. Then negative number. That is how can we represent a negative number? That is positive number to negative number. Or arithmetic logic unit, ALU. And we'll also look about the hack ALU. So first thing is binary number. We know that 0 and 1 are known as binary numbers. And as the number is expressed in a binary or base 2 numeral system, it describes the numerical values by two separate symbols, that is 1 or 0. The base 2 system is positional notation with 2 as a radix. So in this, basically 0 and 1 are known as binary numbers. So now let's see the representation of binary numbers. Decimal numbers from 0 to infinity is represented using the binary numbers with a combination of ones and zeros. 0 is represented as 0, 1 is represented as 1, and 2 is represented as 1, 0. 3 is represented as 1, 1, 4, 1, 0, 0, 5, 1, 0, 1, and so on. Now binary to decimal notation. Here the binary number is given 10101. It is represented to 21. Binary number 1 into 2 to the power 0 and 0 into 2 to the power 1 and 1 into 2 to the power 2 and 0 into 2 to the power 3 and 1 into 2 to the power 4. So on is given up to 21. So by adding all the results, we'll get the sum of 21. This is the representation of binary number into decimal format. So binary number 10101 is represented or resulted as 21 in the decimal format. Now decimal to binary. 14, the decimal value 14 is represented to binary by taking or dividing the number 14 with 2. All the remainders are formed in a reverse manner, like 1, 1, 1, 0. This is the binary representation of decimal value 14. So here we see the conversion of binary to decimal and decimal to binary in a simpler way. Now let's look about what is mean of binary addition and with the example. Binary addition. Basically, a plus a and b as two binary values will perform binary addition on these values. So 0 plus 0. Sum is 0, carries 0. 0 and 1, sum is 1, carries 0. 1 and 0, sum is 1, carries 0. 1 and 1, sum 0, carry 1. So let's see the example. Here we took the two binary values 100, 10101 and 110, 111, 00. By adding these two binary values with from units place 1 plus 0, 1, 0, 0, 0, 1, 1, 0, carry 1. And by a similar way 1, 1, 0, carry 1. Now 111 we are adding, we'll get the result as 0 and carry as 1. Sorry, result as 1 and carry as 1. So now adding 1 and 0, we'll get 1, 0 and 1, 1, and 1 and 1, 0, and carry 1. This is the binary representation of the result. So in this way, we'll perform the binary addition of two binary numbers. Now let's see what is meant by adder and its types. Simpler way is a digital circuit that performs addition of two numbers. So basically an adder is a digital circuit that performs the addition of two numbers. Types of adders. We basically discussed two types of adder, half adder and full adder. Half adder, it adds the 2 bits. Full adder adds the 3 bits. There is a very slight difference between half adder and full adder. Now let's look in detail. Half adder. Half adder. Here in half adder is a pictorial representation and here is a truth table. First let's look at the truth table of the half adder. When we input 0 0, we'll get sum 0 carry 0, 0 1, sum 1 carry 0, 1 0, sum 1 carry 0, 1 1, sum 0 carry 1. In this, here in the pictorial representation, we'll take two input values, A and B, and we'll get the sum and carry generated by XOR and AND gates. So in simpler way, we can say that two input values result the sum and carry by using the half adder. In a similar way, full adder. In full adder, we'll get three inputs, A, B as common, and C, that is the carry as the one more input to full adder. Now let's discuss when 0 0 0, sum 0 carry 0, 0 0 1, sum 1 carry 0, 0 1 0, sum 1 carry 0, 0 1 1, 0 1, 1 0 0, sum 1 carry 0, 1 0 1, sum 0 carry 1, 1 1 0, sum 0 carry 1, 1 1 1, Sum 1, carry 1. This is the truth table for the full adder. So three inputs performs the full adder to compute the sum and carry. So three inputs in inserting in the full adder results the sum and carry. Next topic is negative numbers. Representing the positive number to the negative number. It is a very important topic as here comes the sign bit. So let's take an example of 5. So first of all, representing the 5 in a binary representation as 0, 1, 0, 1. One's complement of 5 is reversing the number as 1, 0, 1, 0. All the zeros are converted to 1 and all the ones are converted to 0. So 0, 1, 0, 1 is converted to 1, 0, 1, 0. Now taking the 2's complement of 5, that is 1's complement plus 1. That is 1, 0, 1, 0. It's a 1's complement. We are adding 1 to it. So it becomes 1, 0, 1, 1. That is a 2's complement. Here, most significant bit, that is 1, represents the sign. If 1 comes, we'll take minus. If 0 comes, it is positive. So representing the positive number to the negative number is nothing but taking the 1's complement and performing addition to it. So first, the binary decimal number is represented to binary number performs 1's complement, that is 0 as 1 and 1 as zeros. Then add 1 to the 1's complement. So here at last we got 1, 0, 1. Last most significant bit 1 represents the sign. So output is -5. Now let's discuss the von Neumann architecture. Here is the von Neumann architecture pictorial representation. Three basic inputs: input, computer system, output. Input is given to the computer system and result is output. Computer system, memory, CPU, etc. Inside the CPU, we have main unit known as arithmetic logic unit, ALU, and control unit. These are the main two important units to perform any computational or arithmetic logic operations on the system. In this chapter, we are basically doing or working on ALU, arithmetic logic unit. Arithmetic logic unit. It computes the functions of two inputs and outputs the result. That is, when two inputs are given and a resultant function is told, will perform the function on the two inputs and result the output. If function f, one out of the family of predefined arithmetic and logic functions. F is known as the one out of the family of predefined arithmetic and logic functions. What is arithmetic operations? Integer addition, multiplication, division. Logical operators like AND, OR, XOR, NOT, and so on. So basically, arithmetic logic unit means performs the basic arithmetic and logic operations. Two inputs, one output, defined on function f. Now, we'll discuss about the hack ALU, that is hacked arithmetic logic unit. It is nothing but we compute the values of 16-bit, that is two complement values. That is operates on 16-bit two complement values and output the 16-bit two complement values. That is hack ALU basically operates on a two complement values of 16-bit size. So two's complement values of 16-bit size are taken as the input and results the output of 16-bit size of two's complement value. Here we have 6 control bits based on its performance. 1 out of the 18 functions are there. It has 1 bit control outputs. Here is a representation of hack ALU. We have two inputs x and y of 16-bit size and one output of 16-bit size. Here we have 6 control flags: ZX, NX, ZY, NY, F, and NO. Here is the output that we told: 0, 1, -1, x, y, not x, not y, -x, -y, x plus 1, y plus 1, x minus 1, y minus 1, x plus z, x minus z, y minus x, and x and y, x or y. These are the output of the hack ALU. Now we'll see the full table of the hack ALU. Table of control bits to the binary combination. That means we have inputted the binary values into the table of control bits. So that is results the following output. That is 18 functions. Here ZX, NX, ZY, NY, and F1, NO are the control bits, and the resultant output. So, for example, if we input ZX as 1, NX as 0, and ZY as 1, and NY as 0, and we give the function as 1 and NO as 0, we get the output 1. Similarly, when you give all ones, output is 1. When you give triple 1, 0, 1, 0, we get -1. Similarly, we get all the operations. So when we give 0, 1, 0, 1, 0, 1, we'll get X of Y. This is the hack ALU table of control bits to binary combinations. That means all the control bits are assigned with the binary operations and resultant outputs have been displayed. Now let's look at the control bits of hack ALU. As we already know that there are 6 control bits, that is ZX, NX, ZY, NY, and F and NO and output. ZX and NX are known as pre-settings of X input. ZY and NY are known as pre-settings of Y input. F selecting between the computing plus and or post setting the output resulting the ALU output. ZX. If ZX, then X is equal to 0. If NX, then X is not equal to X. Then Y, then Y is equal to 0. If NY, then Y is not equal to Y. F, if F, then out is equal to X plus Y, else out is equal to X and Y. No, if no, then out is equal to not out. Out of X and Y. Here pre-settings of X and X input, that is takes the input value and computes the X value. Pre-settings of Y input takes the Y value and computes the Y value. Setting with the computing operations, that is function, has been selected by the F variable, and output is displayed, that is resulting ALU output has been displayed. This is the hack computer operations. ZX, NX, ZY, F, and NO. As we have already discussed that when we assign the binary values to the ZX, NX, and so on of the 6 control bits of the hacked ALU, we will get the output of X, Y as 0. That is 16 functions are represented. Basically 0, 1, minus 1, X, Y, not X, not Y, minus Y, so on. X and Y or X or Y. So let's take the one example. ALU operations. Here let's compute or not X. We'll take two, that is X and Y as input. We'll take X value as 1100 and Y value as 1011. Pre-settings are X 1100, Y 4 ones. Compute and post settings of X and Y. By X and Y we'll get 1100. Not of X and Y we'll get 000011. Not means we're performing one's complement. What is meant by one's complement we'll see in further. No, hack ALU, output control bits. As we already discussed that there are 6 control bits. ZX, NX, ZY, NY, F, and NO. And 2 input bits X and Y, and 1 output bit 16 bits. If out is double equal to 0, then ZR is equal to 1, else ZR is equal to 0. If output is less than 0, then NG is equal to 1, else NG is equal to 0. These 2 control bits will come to play when we build the complete computer architecture. So ZR and NG are also one of the important bits of hack ALU. Here is the complete architecture. So 6 control bits, 2 input symbols, 1 output, and 2 control bits. These control bits come to play when we build the complete computer architecture. In this video, we are going to simulate these 4 topics: hardware adder, half adder, full adder, 16-bit ALU. That is, ALU is also known as incrementer. So we'll perform the operations on hardware simulator tool. Here, as we discussed earlier, it is the symbol that is we use it to load the code to the system, and the HDL code is displayed in the screen shown here. Here is the internal pins, output pins, input pins, etc. This is the symbol where we load the scripts. So first of all, let's load the half adder code. So click on the load. Half adder HDL code is present here, and load script, and it displays the half adder HDL code. Now let's load the load script. That is full examples of half adder. Half adder text. Here all the cases of half adder have been displayed. Now once we click on run, it computes the code. Once the compilation is successful, we'll get comparison ended successfully. So now to view the output, we'll click on view and output. Here is a truth table for the half adder. So let's verify the truth table of the half adder. Here is the truth table for the half adder in our PPT. When we get 0, 0 as the input, 0, 0 as output, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1. Here is the same table. So it is the correct representation or correct HDL code of half adder. Similar way, we'll load full adder HDL code. Load. And let's set the load script of full adder. Here is the load script of full adder, that is with the full cases. So let's run the score. Comparing all the test cases of the full adder. It takes some time, and when it's successful, compilation ended successfully. Now to see the output, come to output and see the output. This is our full adder representation. Here is the full adder code. 3 inputs ABC, 2 outputs sum and carry, and these are the output values 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1. So full adder HDL code is also the same. Now let's load the other thing, that is add 16 HDL or add 16 HDL. Now let's load the load script. add 16 txt. Add 16 txt is loaded into the here. Now let's run it. Running all the test cases of add 16. After this comparison ended successfully, now we can view the output. Here is the output of the add 16 or ALU. Now let's run incremental 16 HDL. This is the lot code we are going to run in this project too. So load script of incremental 16. Here the text cases for incremental 16, and now let's run it. So incremental 16 has comparison has ended successfully. So all the test cases has ended successfully. So all the HTTP scores have been verified successfully. So thank you. This is Vishwadevya Reddy signing off.